Thank you for the introduction. As said, my name is Christoph. I'm a PhD student at the Johannes Kepler University in Linz in Austria. And yeah, thanks for attending this talk. As you see, the title is not that fast and compact, so we will break it down a little bit and talk about ahead of time compiled Java code or GraalVM Native Image as already announced. So GraalVM is a polyglot virtual machine, can execute and interpret different languages. There is an ahead of time compiler there. There's also a just-in-time compiler there. And today we focus on Java code. So how does this work? It's a little bit more described in detail in the paper. In general, you have application code, and you also have the JDK, the library, the runtime, and your methods, your compilation units are laid out there. And GraalVM Native Image performs a reachability analysis, detects unreachable code. This code is then removed, and the rest of the code is then compiled into machine code. So far, so good. And this is also not my work yet, of course. Yeah. And if we now take a look at Java, at this procedure, so we start with Java source code, we compile it to Java bytecode, and then it's further compiled down to machine code, and then we can actually do a size comparison. And so on this diagram, on the x-axis, you see the bytecode size of a compilation unit. On the y-axis, you see the machine code size. All dots on the line mean that the bytecode size and the machine code size are equal, and every dot is now a compilation unit of the DaCapo benchmarks. And as you can see, on average, the machine code is larger. On average, is 3.1x, which means we produce very large binaries if we compile applications. So we might reduce the size of ahead-of-time compiled Java code. And since we saw that the intermediate representation is smaller than the machine code, we might just replace it. So what is happening? We have an application with certain compilation units, and we remove certain compilation units. Of course, to make the program still, or to keep the program valid, we have to add the corresponding code we removed, but we now add it as bytecode, which takes less space than before. So now, of course, we still cannot directly execute the bytecode, so we still need an interpreter, and more information on that later. We also need a JIT compiler to keep performance, but as said, more on that later. But still, if we're lucky, we get savings, and this is what we want to achieve. So small introduction, kind of behind the scenes. How is this working? We have our Java code as bytecode. We apply it to the ahead-of-time compiler. It also does some profiling, so it injects certain data. PGO stands for Profile Guided Optimization, for those who do not know this part. And then the ahead-of-time compiler generates a final executable. What is also created by our approach is a metadata file containing the bytecode of the application we want to compile. And we also extract a list of all compilation units. And for that, we can decide if we want to keep the compilation unit as ahead-of-time compiled code, or if we want to interpret the compilation unit instead and store the smaller version, so to say. And for this decision, which I will talk later on the next slide, we can also use the profiling data, of course. What is then still necessary, and our current approach, this happens at runtime, is to redirect the execution. So at the start of the execution, there's a small initialization phase, which runs over the interpreted compilation units and just forwards the method entry. So there's the global offset table, and that corresponding entry is modified such that if we call a method which is said to be interpreted, then the interpreter starts instead of the machine code which is not available anymore. So now let's look a little bit into these heuristics. How do we currently decide how to execute a compilation unit? So as you can imagine, if we have a very large compilation unit, it makes sense to interpret it in general, because then otherwise it would take a lot of space. On the other hand, of course, we only care a little bit about performance, or not only a little bit. We also have long-running application units. And since we already have the profiling data available from the GraalVM Native Image compiler, we can detect compilation units that are long-running. For example, they contain a loop. On the other hand, there are compilation units that are called many, many times. These are also detected by the profile. And if we just put those three numbers together, we get a rather simple but useful metric, which kind of estimates, so we get a number, and that number can tell us if it might be better to interpret it or if it's better to keep it ahead of time compiled. So as you can imagine, there is a trade-off between size and performance. And what we can do is we have our application with all these compilation units, and we can sort those compilation units by our metric number. Then I plotted this on a diagram here. So at the x-axis, you have the code savings, so how much were we able to reduce the code. And on the other hand, we have the execution time of the application. So when we start, of course, we don't have any code savings, and we get a certain execution time. Then, for example, we can decide to remove the compilation unit h, save some space, and then execute it. And then, for example, we see that h is not performance relevant if we interpret it. So rather lucky. It can also happen, however, that we remove the next compilation unit, and then we see that performance increases. So now we are at an unlucky state. We can proceed this analysis. Of course, we don't have to do this for every single compilation unit. You can also remove them bucket-wise. Then you get a diagram kind of looking like this. Of course, our goal is to be at the right bottom part, because there we achieve greater code savings while execution time is still low. Short side remark on that, not every code can be interpreted. One reason is, for example, you cannot interpret the interpreter. So this was one of the first things I discovered. Yeah, I just ran into a Stack Overflow, because if you want to interpret the interpreter, of course, this does not work out. And there are also some other code parts that have to be ahead of time compiled. Those are just known by a whitelist or by a block list, and then you're safe to go. So I'm also teaching basics of software development, and just took homework where the students had to implement a single linked list, and also tried our approach with this very simple application. And there we could get such a diagram. So now you see the resolution is way more higher than just 8 compilation units as on the previous slide. And we can see that there are a lot of irrelevant compilation units. So when we interpret them, there is no real big change in performance. However, the linked list add method, it's just one compilation unit, but it doubles the execution time. And our simple metric was not able to detect that, kind of. And we also realized that we will never be safe if we just use heuristics. It can always happen that we are unlucky and just detect such a small method that really causes problems. So further to approach the full title, of course we don't want to sacrifice performance. And for that we take a look at the execution modes in general. So for our current approach, we combined ahead of time compilation and interpretation. So we are kind of moving along this axis. We started from ahead of time compilation and then went on further. And as you can see here, ahead of time compilation achieves a high peak performance. On the other hand, interpretation leads to small file sizes. However, we can actually complete this triangle and insert just-in-time compilation as well, and try to move inside the triangle. So instead of pick 2 out of those 3, we try to get the best of all 3 by applying just-in-time compilation and by saving the performance. However, before really implementing a cheat compiler, we simulated it first, just because of a research question. If we include it into the final product and then we realize this doesn't really work out, it's a lot of wasted time, and therefore it's a rather cheap simulation. So what we do is, because we have to decide at runtime if we want to cheat compile a method, what we currently do is we just take the time between 2 subsequent calls of that compilation unit. If it's large enough, we continue. If this is below a certain threshold, we just cheat compile a method, And JIT compilation means in this case, we just replace the bytecode again by the ahead of time compiled machine code. So this is no real JIT compiler, this is just a simulation, but you will see in the next slide that it's not as bad as it sounds in the first place. So on the left we have a diagram of the DaCapo FOB benchmark, which does PDF layouting, and there it's the same approach as before. We remove compilation units and then just take a look how performance evolves. And if we now add our JIT compiler or our JIT simulation, we see that the performance is way better. Please mention that the x's here are different. So I noted the 130 line in the left diagram. What we can also see that the deviation gets a little bit stronger. But on the other hand, you see that with only JIT compiling 5% of the interpreted compilation units, we can actually achieve a way better peak performance. And this is also a reason why we saw that this is useful, because 5% are not that much. So just by removing very few methods, or compilation units again, and JIT compile it, we keep peak performance. And this is also, so we don't have concrete measurements for warm-up performance here, but since it's only 5%, we claim it to be not very large. Another aspect I would like to emphasize about our approach is that the savings need to compensate the additional code. What do I mean with that? So again, there's a diagram. The machine code size of the original application is the x-axis, and the code savings are on the y-axis. So code savings is the difference. You have the original machine code, then you remove some parts of the compilation units and add them as bytecode instead. And this is the difference, what I call code savings. Of course, to be able to still execute the program, you have to add the interpreter and the just-in-time compiler. These are constant 14 megabytes, and you see the pay offline here in this diagram, which means, for example, if we have an application of 100 megabyte, we see that we have to kind of save 15% of the code savings such that our approach pays off. Of course, for very small applications, the interpreter overhead and just-in-time compiler overhead is very high. And on the other hand, for larger applications, size reduction is achieved really fast. How does this look like for concrete benchmarks? So here you can see the DaCapo suite. Again, the FOB benchmark is achieves one of the best results because it has very large file size, 180 megabytes if you compile it to machine code. And as you can see, we could achieve 44% of code size reduction. If we add the interpreter and the JIT compiler again, we have a reduction of 37%, which is quite nice. On the other hand, the LO index benchmark, for example, we could save 10% there, but since it's a rather small benchmark with the overhead, we produce an even larger file. So for smaller applications, our approach is currently not really, or does not really make sense to use. However, if you think about the cloud environment, for example, also the Spring Pet Clinic benchmark is added here. We could achieve 20% of the code savings. So if you use less memory to save the file, it's also usually lower costs. Some comments on related work, because I'm not the first person who tries to mix execution modes. Also for Java code, the Android runtime does something similar, but they're doing actually from the other side. So they start with interpretation and JIT compilation in the first runs, and then in subsequent runs, they also detect code which should be ahead of time compiled. It's not that they don't focus on file size at all, but I said they approach the direction from another part, because we are starting directly from the ahead of time compiled code. There are also different research groups. I summed it up with JIT caching that try something similar as well. Some of you have heard maybe about Project Leiden. So they are also trying to include ahead of time compilation into Java execution. This is still in development, not in the very early stages, but as I said, still in development. And maybe some of you has also thought about native extensions where different execution modes are mixed. The things for native extension is that the execution mode is selected manually by the programmer. So for example, if you think about Python or Python and C, where those languages are combined, as a programmer, you decide by the programming language how it is executed. So C code is ahead of time compiled, while Python, on the other hand, is interpreted and just-in-time compiled. And last year at VML, we showed an automatic approach where we could actually also improve the results. So we could take an existing Python or Python application and prove that our manual detection of the execution mode actually works better than programmers letting decide the execution mode themselves. So what I would also like to mention is that my approach is not, not finished yet. One of the most interesting things concerning research, in my opinion, is how important is profiling data. So in the current approach, it's easy to know how large the compilation units are because this is not in compile time. But currently, as said, we rely on profiling data. And it would be nice to get rid of those profiling data. The question is, how important is it? How much worse do we get? And can we get to a reasonable approach without this profiling data? So this is my most important interest currently to improve soon. And with that, I clicked on the wrong thing and might get to the correct slide again, but I'm almost at the end. So what did we see? We see that Java files can get really, really large. However, we can shrink file sizes by just removing ahead of time compiled code. And at the intermediate representation again, we have some decision progress and some heuristics, which currently work quite well. However, the question is, can we, also concerning JIT compilation, we achieve quite nice results for larger files. The question, as said, is how do we perform with our profiling data? And with that, the presentation is actually a little bit faster than expected. But now I would hand over to the question and answer part. Thank you.
Thanks, Christoph. Let's take some questions, please.
These are an important criteria here too. So one question. Mm-hmm. You mentioned, the premise is that AOT-compiled code is larger than bytecode, and hence files, shrinking file size is important. So how does, in general, for Java programs, real Java programs, the size of the JIT compiled code compare with AOT? And if it is less, how does it differ from reusing JIT cached code? You just mentioned it briefly, but I would like to hear more on it.
As said, we're currently only simulating a JIT compiler, so it's only a proof of concept that it makes sense to include it. But we actually have not included a JIT compiler directly. Okay. So currently we are just switching back to the larger code, which is of course not nice for file size. If we keep the JIT rate, so to say, low, because it's 5% for all of the benchmarks, or below 5% actually, then we also see that the effect on the file size is not that high because it's not a lot of methods that are JIT compiled.
Okay. But in general, would you can we assume that JITed code size would be lesser than AOT compiled code? You have PGO, but fewer optimizations.
It's a good question, depending on the speculation part. So if speculation, for example, works nice, then I can imagine that the size gets smaller. In the worst case, it gets as large as the AOT compiled code. But I cannot give a concrete answer to that, unfortunately, no. Thank you.
Small question. Let me clear the motivation. So you want to reduce the size of the ahead of time compiled code. Mm-hmm. So why do you want to reduce the size? So the storage price is relatively cheap. So why do you want to reduce the size of the compiled time?
If you compare it to other file sizes or to other execution modes, the size is still larger. For example, also on on your phone, you could fit more apps if the space is already full. If the app would take less space, and also for cloud environments, it's.
I see. So not for the server side, but for the devices, something like that.
Sorry.
So this research is for the such a small devices, not for the server side applications or something like that.
So our application works better for the for larger applications. Our approach, but also for server size. Of course, you pay less if you need less space.
Thank you.
Yeah. So I'm also curious about the motivation. So for the leftmost picture, so it's just-in-time compiler is included in the native code, native image. So I think, but just-in-time compiler just generates more code than you expected. So how do you think about the compensation about the JIT code, JIT just-in-time compiler generated code?
And currently, we only use the JIT. So in this calculation, we only included the JIT for the sizes. For a real application, of course, as said, the JIT rate is rather low. So we really use the just-in-time compiler only to compensate the errors of our heuristics. So it's not the goal to just-in-time compile all of the compilation units, but just if our heuristic does not, or thinks that we should interpret a compilation unit which is really performance relevant, only then we use the JIT compiler to wipe this error kind of out. By that, the influence is not that high on the total memory.
Okay, thanks so much.
A last question, please.
I wondered, are you storing the compiled code in a compressed form, or is it just stored plain in the executable?
Currently, it's just the executable. There is another PhD student in Belgrade, I think, who tries to compress certain code. So they have the drawback that they have to uncompress code again if they need it. Of course, on the other hand, if we do a wrong decision, then we have a bad performance. If they do a wrong decision, they have the advantage that they only have to unpack it once and then have the full performance again. So we haven't considered compressing it yet.
Thank you.
Let's thank the speaker again. Thank you.